Welcome to the deep dive. Today we're going to reverse engineer the design philosophy behind Java.
Mhm.
We're talking about object-oriented programming OP. Not just the definitions, but how it dictates the way, real scalable applications are actually built.
That's right. And this is really for someone who's already in the trenches. A working developer.
Hmm.
We're not asking what encapsulation is.
Right.
We're asking how you use it to stop technical debt from piling up.
Yeah.
We're looking at the kind of blueprint an engineer like Syed, a developer in Hyderabad, would use to design a stable system.
So our mission today is to unpack this single, really dense source that covers the whole landscape.
Yeah, everything.
From the big four principles all the way down to the tiny keywords, we want to give you that actionable architecture manual,
Mhm.
move past the textbook stuff.
Exactly. At the end of the day, OOP is just a way to organize complexity. It's about structure, about turning this sprawling mess of code into components you can actually predict and reuse.
Okay, so let's get into it. The pillars. Every OOP discussion starts with the foundational four. Let's start with the first two, encapsulation and inheritance,
Encapsulation. So the simple definition is just wrapping data and methods into a class.
which is fine, but
The real insight here is it's about creating a clear contract. It's really the defensive mechanism. You're protecting your object's internal state from the outside world.
and the way you do that is with the access modifiers,
Yeah.
right? The private, public, protected.
Exactly. You're hiding the details. You're basically telling other parts of your code, look, you can use my object this way through these methods I've exposed.
But you cannot touch the data directly.
You can't mess with it.
Yeah.
And that maintains data integrity. It prevents all those weird, unpredictable side effects you get when things start interacting in a big system.
And that reuse idea, that leads us straight to inheritance.
It does.
The definition is simple. A child class gets properties from a parent class. It's like the original engine for code reuse in programming.
It is, and it's so powerful. It lets you specialize. You can define a general vehicle class, and then a car or a truck can just extend it, and boom, they inherit start engine.
But there's a catch, isn't there? This is where it can get messy.
Oh, absolutely. This is where you run into major architectural headaches if you're not careful. It creates this really tight coupling between the parent and the child.
You're talking about the fragile base class problem.
That's the one. You change one little thing in that parent class,
The base class.
the base class,
Yeah.
and you could just completely break something in a child class
Uh,
in a way you never predicted, which is why a lot of big companies are, very careful about how they use it.
so if that's the danger, there must be a design principle to sort of keep it in check.
There is. It's called the Liskov substitution principle, or LSP.
Okay.
And all it really says is that a subclass has to be able to replace its parent class without causing any problems. It can't break the contract.
So if the parent method says it will never return null, the child method better not return null.
Exactly. That's how you design for stable extensions, not for a maintenance nightmare.
All right, let's get to the next two pillars, polymorphism and abstraction. This is where, for me, the real aha moments happen.
For sure. Polymorphism just means many forms. It lets a single method or interface handle different kinds of behavior. It's what makes your code adaptable.
And Java gives you two ways to do this, right? It depends on when the decision is made.
Right. First, you've got method overloading.
The easy one.
The easy one. Same method name, but different parameters. The compiler figures it all out before the code even runs. It sees the signature and binds to the right version. That's your compile time polymorphism.
But the really powerful version is method overriding. That's when a child class redefines a method it inherited.
And that decision can't be made until runtime. The JVM has to actually look at the object when the code is running and say, okay, which version of this method do I call?
And that's dynamic polymorphism.
That's the dynamic stuff. It's the core of how frameworks like Spring work. You have one interface, dozens of implementations, and the system just picks the right one on the fly. It's incredibly flexible.
That flexibility leads perfectly into abstraction.
It does. Abstraction is all about hiding complexity. It's about exposing only what's essential. The goal isn't just hiding data that's more encapsulation. This is about hiding the process.
So as a developer, you just want to focus on what an object does, not the 1,000 lines of code that make it happen.
Precisely. You call process data on some file handler object, and you don't care if it's using fancy new I/O streams or old buffered readers. You just care that the data gets processed.
So how does Java enforce that?
It gives you two main tools, abstract classes and interfaces. And, developers often get these two confused.
Interfaces used to be super simple, just method signatures, no code.
Right. They were just pure contracts. And they were the only way to get around Java's single inheritance rule. A class can implement multiple interfaces.
But that's changed a bit, hasn't it?
Yeah, since Java 8, you can have default methods in interfaces, so they can provide some base functionality. But the key thing is still that ability to implement many of them. It's perfect for defining loose contracts.
And abstract classes, how are they different?
They're more like a partial implementation, a template. You can provide concrete methods that all the subclasses will share, like, say, a logging method.
But you can still force the subclasses to fill in the important bits.
Exactly. You use abstract methods for that. Choosing between them is a big architectural decision. An interface is about what an object can do. An abstract class is about what an object is.
So we have the philosophy. Now let's get into the nuts and bolts, the actual components that make this all work.
Right. Let's start with the basics. Classes and objects. The class is just the blueprint, static. It defines the fields and the methods.
And the object is the real thing. The living, breathing instance of that blueprint that's actually running in memory. It's Syed's specific laptop object.
Exactly. And the thing that gives it life, that brings it into existence, is the constructor.
And its job is just to make sure the object starts in a valid state, right?
That's its whole purpose, initialization. But the really powerful part for developers is constructor chaining.
Using this or super inside a constructor.
Correct. When you have a subclass, if you don't explicitly call super to initialize the parent,
The compiler sticks one in for you.
it does. It inserts a call to the parent's default constructor. And if the parent doesn't have one, your code won't even compile. That sequential chain is how state is guaranteed all the way up the hierarchy.
That's such a critical detail. The super call has to be the very first thing. It guarantees the base is fully built before the child starts adding its own stuff.
So moving on from single objects, we have to talk about how they relate to each other. And this is where composition versus aggregation becomes so important for managing how tightly coupled your code is.
This gets glossed over a lot, but it's huge. Let's start with composition.
Composition is a strong has-a relationship. Think of a car and its engine.
The engine can't exist without the car.
Exactly. Their life cycles are tied together. If you destroy the car object, the engine goes with it. They're tightly coupled,
And then there's aggregation.
which is a much looser relationship. Think of a department and its employees. If you get rid of the department, the employees still exist, right?
Right, they can be moved to another department.
They can. The components can live on their own. And the architectural implication is massive. Aggregation usually means looser coupling, which is almost always better for testing and for flexibility.
So we've covered the big principles, the relationships. Now for the keywords, the tools you use for control.
Back to the gatekeepers, the access modifiers. We talked about private and public, but protected and the default one are often misunderstood.
Protected is for subclasses and anything in the same package, right?
Yeah, it's a careful balance. You're hiding details from the whole world, but not from your direct family, so to speak.
And default, the one with no keyword.
That's package private, only visible within the same package. It's an amazing tool for encapsulating a set of related classes without exposing their internal workings to the rest of the application.
Okay, beyond visibility, we have keywords that change how things behave in memory. Let's talk static and final.
Static members belong to the class itself, not to an object.
So there's only one copy shared by all instances.
Exactly, which is great for utility methods or constants. But it can be really dangerous if that shared state can be changed, because then you have side effects that can pop up anywhere in your app.
And final, the ultimate control keyword.
It is. It locks things down. A final variable is a constant. A final method can't be overridden. And a final class.
Can't be inherited from at all.
Which seems like it goes against the whole idea of OOP, right? But think about a class like string in Java. You do not want anyone messing with its behavior, so you make it final. It's a deliberate choice, stability over flexibility.
So tying it all together, what does this actually mean for you, the developer listening?
It means you're moving from just writing code to actually building systems. By really getting the trade-offs of inheritance, why LSP is so important, how to choose your coupling. You gain the structure you need to design applications that aren't just working today.
But are clean, scalable, and maintainable a year from now.
Exactly. That's the whole game.
We've covered a huge amount of ground here, from the big philosophical ideas down to the nitty-gritty of the keywords.
And Just to leave you with one last thing to think about,
Hmm.
a provocative thought.
Oh.
We talked about how the Liskov substitution principle demands that a subclass must honor the parent's contract.
Mm-hmm.
And we also said that the final keyword completely prevents inheritance and modification. So here's the question. If you have a critical base class with behavior that absolutely must not be changed, how does making that class final actually reinforce the goals of LSP by preventing bad substitutions, even though it seems to completely shut down the principle of inheritance?
That's a great question, a real design conflict to wrestle with.
It is, and it's something to mull over as you architect your next application.